Good morning. Let's get started. So today the programming assignment is due, right? And we're moving on. This week you'll learn everything you need to know for the next one. How's it going with the programming assignment 2? Any questions on that? Is it fun? You're drawing those curves. Some questions. You can use my functions for that. You have to learn how my functions work, of course. And I told you last time about parametrized curves, which I won't have time to talk too much about. But review your Math 53 if you're confused. I think many people will be confused about x, y, and t, because x and y are now functions of t. But it shouldn't be too confusing. We are here. We're doing chapter 4. And by the way, just for the future here, it's 2.5 weeks to the midterm exam. I think I told you last time we'll cover everything up to that's been covered on homework before then, which is going to be most of chapter 4. But I'll post later exactly what's covered. But just so you know approximately, that's what the plan is for the midterm exam. But coming up pretty soon, I guess. And we'll also have, just before the midterm, this programming assignment on splines, programming assignment 2 will be due. And that's will also be covered on the midterm. And of course, we discussed it before, it's hard to ask you to write long codes on a midterm. But I still say that it is covered. It's part of it. And maybe I can ask some questions. But you'll see from old midterms that I post that it is difficult to ask coding questions in general. Let's go on. Also, sorry about that mistake in the bug with the spline for today's homework. But it's good. It makes you think a little bit. Obviously, we don't know how to do f prime somewhere else. I don't have the spline. The only thing we know how to do with splines are two conditions, right? Natural, which is second derivative 0 at the edges, or clamped, which are derivative are given. So it was obvious that problem that you had due today was wrong because it gave the derivative even outside the interval, right? So it's good. It makes us think a little bit. What's more unclear is what they actually want us to do. And I told the GSIs it doesn't really matter. As long as you do something, you'll get, they will be fine with it because the problem was wrong. But the idea is we just know how to do that. Specifying a derivative outside is double bad because these polynomials are not even defined out there. Remember, splines was polynomial, polynomial. You just can't say the derivative should be something out here. It's just obviously wrong. So, but having said that, I don't know exactly what they wanted because that number in the I don't know what that was. Anyway, so we left that, everything in chapter 3 was interpolation, drawing polynomials through points, basically, right? Possibly matching derivatives, possibly doing the spline trick of having many different polynomials. But the idea is interpolation, or sometimes extrapolation, the idea of fitting and interpolating through points. Chapter 4 is going to be how to compute derivatives and integral numerically. Another big topic in standard traditional numerical analysis. And if you just want the motivation, I already told you about differentiation. That's the smaller part. But suppose you run Newton and you don't know the derivative. Taking derivatives can be quite messy. Maybe you don't even know the function. How could you possibly differentiate it if you don't know the function? But integrals are even more extreme because you know that there are very few integrals you can compute. Gaussians, for example, for statistics, e to the minus x squared, we just don't know how to integrate it. Okay? So here it's a huge topic with numerical integration. And it's a well-developed field, so you'll learn some excellent techniques here. We started talking about differentiation. It's just one section on that. This you should have seen before. It's called the forward difference approximation. It's claiming that you can approximate the derivative of a function f at a point by stepping h to the right and subtracting the f values dividing by h. Why can you do that? Well, you can see it in many ways. One way is to draw a picture and see that if h is small, that should be good, right? The other is to say that it's really directly inspired by the definition of the derivative. Of course, there the h is supposed to go to 0, which we can't do in the computer for numerical reasons, but small enough might be OK, right? Now, to make it more precise, what did we do? We plugged it into our Lagrange polynomials. What we actually did, just to get the error term out, was to say that you're standing here, you're taking a big, normally it wouldn't be this big. I'm just drawing it like this to make it more clear. So whatever way you want to see that this is a good approximation, but in order to get our hands on the error term, we went back to Lagrange. And we said, it's a straight line between these 2 points, right? We wrote it down, and Lagrange, back in section 3.1, gave us an error, and we could differentiate that error. And with some luck, in particular plugging in point x0, we could get the number out. And that number ends up, of course, being xi, we don't know. But I think you shouldn't be too surprised about this form. It's a it's a lot of understanding can go into that form. First of all, it scales linearly with h. It's first order in h. It's not so good, but it can be understood that if you divide h by 2, you're not happy with the slope. You think that it's too far away from the true derivative. And you divide h by 2. How much better does it get? Only a factor of 2, right? That's what it means by linear in h. So, it's getting better, but maybe not fast enough. So a better method, you divide h by 2, maybe the slope that you estimate would be 4 times better. That would be a better method. The other part that is clear here is that it scales with the second derivative of some xi. Is that clear? Well, it's not completely obvious, but you can convince yourself that it's not obviously wrong, at least, by thinking, what's the error if it's a straight line? How bad is this if the truth f is a straight line? It's pretty good, right? And it's perfect. So that makes sense, because then the second derivative is 0. How good is this for a parabola? Is it perfect? No. The true derivative is this, and this gives something else, right? So it's not perfect for a parabola. So it seems like the first higher-order derivative that should show up would be the second one in the error term. You can just convince yourself of those things. And you'll see that more in the future things, that we will actually kill off that term as well and keep on going. Of course, you can go to the left, and we call it a backward difference. The general framework is this. Fit a Lagrange polynomial. You can do more than 2 points. What we want to do, we want to make it better, for example, by putting a point here. And I should call this x0 plus h. You can put another point here, and then you can start thinking about what you want to do then. And, well, now it's messy, but it doesn't matter. You can put any points, and you can derive a new derivative rule. And the general procedure is fit a polynomial, differentiate. And that's done on this slide. Here is the polynomial from this is just exactly the Lagrange polynomial with error term. And we just differentiate. And you can see when you differentiate this, you'll end up differentiating these L's that were 1 at one point, right? So this shouldn't be a big surprise. So actually getting the formula out is just a question of setting up all these L's and differentiating. So it's easy to come up with the rules. Not so easy is to handle the error term. Turns out that, again, that little magic shows up. That means you can actually write it in a nice form like this. But you still have to estimate these terms here. But this leads to the general forms. Some important special cases. We limit ourselves to equally spaced. It's not at all needed, but why not? Just to keep it simple. But if you want to, you could certainly derive a formula where this is different from that. 3 points, whatever you want. This is very general. But now, in order to get more generally applicable methods, it's very common that you have equally spaced. So basically, we have an x. In the first formula, we have an x0, and we have an x0 plus h. And then, because of equally spaced, we have an x0 plus 2h. This is called it's called maybe the 3-point one-sided derivative. One-sided because you stand at x0, and you just look to the right. Okay? And I mentioned that's useful if you're not allowed to look to the left of x0. It could be a boundary. How accurate is this formula? You would expect it to be better than the forward difference, and it is. You have a square of h there, and you have this here, which means in particular that if you run it on this guy, it will be, what will the error be? If I run that formula with any h, remember that formula needs 3 points, x0, x0 plus h, and x0 plus 2h, right? And it does its magic. And it produces, so just looking at the error formula there, without thinking of where it came from, we can see that it's going to be perfect. I'm pretending that this is a quadratic. We can see that it's going to be perfect because the error term involves the third derivative of f, which is 0 for any quadratic. So it's a better formula. We can also say that if I divide h by 2, I'm not going to draw it, but suppose you divide these and get closer, it's going to be 4 times better if I divide h by 2. So it's a better formula. Of course, the second formula, no, the third formula does the same thing, but it looks to the left. Obviously, that's possible. It's not even interesting. But that can be useful if this is a wall and you can't go to the right, you look to the left. Okay? And the middle formula is very common. It says, why don't you do h to the right and h to the left? Probably a formula you might have seen already in calculus, that you do these 3 points instead. And then it becomes the midpoint, and it's symmetric. If you have no reason to go right or left, why not just be symmetric? And you could argue that it's not a 3-point formula, but it is. It just happens to cancel out the midpoint there. So that's a very common formula. And again, and you can actually see a little bit from these error terms that normally we don't care that much about this constant. But you know, this seems to be twice as good approximately than these. So that's good. All right? And before going to the second derivative, how about 5 points? Well, you just turn the crank. It's not even interesting any longer. You just keep on doing it, right? Whatever formula you want. But suppose you want even more accuracy. Throw out 5 points. Take all of these. 1, 2, 3, 4, 5. Obviously, you can now fit the 4th degree polynomial and differentiate that, and you get a really accurate method. And you see it uses all these 5 points in some combination that is not obvious. It has an h4 here and a 5th derivative of f. So you can imagine how accurate this is. In fact, you don't even have to have h very small for this to be accurate. A quick MATLAB demo would be, you know, I love my e to the x, right? And why don't we do h equal? Because we did that last time, and it wasn't that accurate. All right, so what does it say? 1 over 12h times f of x, let's do 0, minus 2h. Let's first do the forward difference. So the forward difference would be fh minus f0 over h, right? It's pretty bad. It's 0.05, it's 5% error. And of course, we can bring it down by reducing h. But let's say this is a reasonable h. How good will this guy do? Well, it will do this, right? I'm just copying the formula at the bottom in MATLAB language. Minus h times 0 plus h minus f of 0 plus 2h. All right, that's it. I messed something up. Times. All right, let's try that. So you see, well, of course, for error, we want to do this, right? Now the error is a 3 in a million, right? It's pretty accurate. It's kind of insanely accurate. And sometimes it's not needed, but these higher order formulas can be useful in many times, especially when solving differential equations. All right, another extension. Now we can do any points, whatever we want, right? How about higher order derivatives? And I did another technique for that. You can kind of derive similar Lagrange expressions. It's just that keep on differentiating this becomes messy with these error terms. An alternative technique I used to derive this very famous and popular formula was this. It's just a different technique. We write out Taylors. We're going to do a lot of Taylors in the future. So f at x0 plus h can be written as a Taylor around f of x0. So f of x0 plus f prime of x0 times h plus, and then you get higher orders of f and higher powers of h. Okay? And it turns out if you now write x0 minus h, you get these alternating signs on every second one, because h is now minus h. So how can we use that to our advantage? Remember, what is the setting? What is numerical differentiation? The idea is that you're giving me function values at points, no derivatives. You're giving me function values, and you ask me to estimate a derivative, right? Well, look at this. This is a function value at the point. These are function values at points. This is, of course, just f(x0). This is stuff you have. Okay? And if you now want f prime, you could derive that from here. But let's say we want to do the second derivative. Then you want to eliminate this, which is very easy in this form. You just add them, and you kill that term off. So you see that if you add that, and you get 2 of this, you get your derivative here times h squared plus higher order terms. That's how simple this trick is. Or if you move things around, the second derivative of x0 is 1 over h squared times the sum of these outer points minus 2 of the mid ones. Very easy way to derive the formula by just doing Taylor and killing what you don't like. But it's nice to identify the fact that we're trying to estimate a derivative. Previously we did this. Now we're trying to do this guy, which means we want to kill this. This is stuff we have because we wanted to write it in terms of function values. The error term was a little bit more tricky, but I went all the way up to h4 last time. I don't want to write it again. And there was a xi. And I think it came out of this perfectly well. The only issue is that it was a sum of 2 xi's, and I had to use the intermediate value theorem to replace it by 1. But that can be done. You can see the book for the details on that. And I did it last time, I think. Went a little quick. So this is the famous 1 minus 2, 1 formula for second derivatives. And it will show up a lot. And of course, you can keep on doing this in many ways. You can get 4-point formula, but the book doesn't really go much further than this for second derivatives. Here's was a nice little demo I did in MATLAB. It's actually interesting to ask yourself, why not set h equals to something very, very small? Or more detailedly, what should you set h to if you can choose whatever you want? And here's an example. Suppose you have the center difference formula. It's a very good formula for the first derivative. Remember? Step to the right minus step to the left and divide by 2h, right? And we have the error formula here, which said this. We looked at that before, h squared in the third derivative. What's the optimal h? What are the issues? And the issues are that smaller h, from how we present it, the smaller the h's, everything gets better, right? I mean, it's clear. Look at the error formula. The smaller h, the better it is. So why don't we set h to 10 to the minus 100? Well, that goes back to section 1.3, round of errors in a computer. That when this h gets small, something bad is going to start happening. In fact, you're getting this cancellation that we talked about all the time. And you can actually analyze this, but first I just ran this demo ahead that did this. I'll tell you what it does. On the x-axis here is my h. On the y-axis is my error, and it's a log-log scale. So if I set h equals to 1, we all know that the error is not too far away from 1, which is bad. It's like 100% error, right? Or maybe a tenth, but it doesn't matter. It's not that accurate, right? And then you keep on decreasing h down to, let's say, 10 to the minus 5. And then you're getting an error of 10 to the minus 11. It's amazing. So that seems to be a really good value, 10 to the minus 5 for this case. And it will give you a great error. But what's interesting is that you would think it gets even better, but no. Now it starts this random pattern going back up. So that if you set h to 10 to the minus 15, remember that's almost the epsilon we had back in 1.3, then you get almost 100% error again, or 10 or something, order 1 error. That's very interesting. And it's because of this phenomenon. It can be analyzed with really just one formula, saying that every time you do a subtraction, you introduce an epsilon of error. But then that's divided by h. That's the issue. The big issue here is that it's divided by h. So even if this here is just introducing an error of epsilon, which you remember is like 10 to the minus 16, you're dividing by h. Which means that at some point when h is too small, that's going to become a significant factor. If h is not too small, this will be a significant factor. So a simple model of this is to say that this comes from rounding error, and this comes from what's called truncation, namely the method, right? And there's obviously an optimal h. And how do you get it? Just calculus. 1 over something over h plus h squared times something. It's calculus. It's just you find the optimal h, and it turns out to be this expression. That's kind of nice. I'm plugging in the MATLAB thing. So it's the cube root. So our epsilon is, remember, 2 times 10 to the minus 16, right? So basically 3 times epsilon divided by, OK, so what is m? Well, that's just a bound on this third derivative. So that depends on your method, of course, right? So if you're differentiating, but in this test, I'm just doing e to the x, as I always do. So let's say that e to the m is really just, that m is just 1. It's a bound on the derivative. So then you get this expression to the cube root, which is, let me just see why that is not exactly the same as I had before. Oh, it used 1 to the 16. In my script, I used 1 to the 16. That's not epsilon. It should be 2 to the 16. Anyway, it gives us this number, which is about 10 to the minus 5. So isn't it nice that you might see this, and you might, first of all, be confused. It shows why some theory is nice to have, because you can actually predict that optimal h that you should use. Okay? This will change if you change formula. So if you do forward difference, it will be lower, because the numbers work out differently. Anyway, now you know everything about differentiation. Here's another thing, Richardson extrapolation. A very common trick, we'll use it in particular for integrals. And you should think a little bit of Aitken. Remember, Aitken took a first-order convergent series, and it eliminated terms, so it became second order. We're going to do exactly the same thing, but with h's. And it's actually quite simple. So here's how Richardson does this. You're going to pretend that you have a first-order series. And if you want to, pretend that it's the forward difference. You're computing something that depends on h, and it's kind of bad because the error is order h. Okay? So what that means is that, so this is called Richardson extrapolation. It's not extrapolation of functions, like in chapter 3. This is extrapolating in h, which is a little different. So it's a confusing name in a way. Suppose you have some number. This is a different n. You have some expression that depends on h, and it's trying to compute a number. So think about f prime. The derivative at x0 can be approximated by one of these forward differences, for example, right? But it's not exact, so you're getting an error, which is ordo h, a constant times h, right? And of course, there are high order terms, so let me keep on going. All right? And in Aitken, you took 2 steps, and you got 2 equations that you could try to eliminate things. Here, we do 2 steps by dividing h by 2. But you can do other things. You can divide it by 3. But in this example, let's divide it by 3. So this means that this is also exactly true, that you can plug in h half, and it's still an identity, right? I said it was exact, so this should happen. And now you're getting h squared over 4, and you keep on going over 8, right? So now you have 2 data points. You're computing, for example, your differences for 2 points. And you can see what we can do, right? You can take the output and do some manipulations. And the goal will be to kill the worst error term and try to get some better result. So let's try to eliminate this one here. The way we do it, if this is equation star, and this is equation double star, you do 2 times equation double star minus equation star to get that m. So 2 of this minus that gives me an m here. And then you're getting 2 of this guy minus this guy. Right? And you can see that this becomes 2 times h hat. This becomes k1h minus k1h. I'm killing this term. That's the reason I did 2 minus. So the next term is going to be k2. And I'm getting h squared quarters minus h squared. And we might need another one, depending on how far I want to go. But you can get an h cubed to the, well, you have to think a little bit here. But you're multiplying this by 2. So it's h cubed divided by 4 minus h cubed. What does this tell you? Suppose that this is all you do. You to compute 2 difference approximation. If you take 2 times the more accurate one minus the less accurate one, you get a new number. That really is a good approximation to m. How good? Well, much better than the other ones, because the first error is scales like h squared. So for small h, it should be much better than these ones. This is the way to accelerate. Accelerate is a word you can use here as well. But it's called extrapolate because you're taking 2 h values and you're trying to go to h equals 0. But you're not really doing it. So why not just keep on going here and call this n2? So this is n2 of h. Let me write it out in more detail here. So n2 of h, we just said, and for future, just to write it to get a nice pattern here, I'm going to write it as this, and then plus that. Okay? But it's really just 2 times the more accurate one minus the less accurate one. It's a great idea. And what can you do? You can, of course, keep on going by doing 2 of these guys, okay? And I'll show you the big pattern later, but let's just do the math for the next one. Suppose now that this n2 of h is approximating m very well, in the sense that the leading order term is minus 3/4 of h squared. Then we have the following. I know, I messed this up. Thank you. This should be a half. That should be a quarter, because I multiplied that by 2 when I did this subtraction. Sorry about that. So this is minus h squared half. Okay? So that's what goes here. So it's k2 half h squared. And then we'll keep on going. You have to do the next one. Turns out to be k quarters of k3 h cubed. And you might want to keep all of these guys, but I'm not going to. But the idea here is really just to see the pattern. Here's another one. Where do you get that one from, by the way? Think about that. h squared over 4. And then we get minus 3. You got to kind of make sure you get this right, but it's. All right, so what am I doing now? I computed n of h and n of h half, and I said I can produce an n2 of h that is more accurate. If I'm happy, I'm done. But I'm not happy, so I want n2 of h half as well. And of course, that's done by doing another n of h quarter here. You can see that the h here is anything. So this formula can be applied to h and h half, but also to h half and h quarter. And that will give me 2 values for n2 that I can do this with. And I do exactly the same tricks, it's just that the numbers are going to be different. So if this is triple star equation, and this is 4 star, then now it turns out you have to do 4 times the 4 star minus the triple star. And that will lead to, I'll go straight to the division away, but it's going to be m is equal to 4/3 of n2 of h half minus 1/3 of n2 of h. All right, plus more. But the same thing happened, that if you have these n2s that you think you're happy with, because they have a leading term of h squared, you can kill h squared and make this even more accurate. So now the next term is a cubic term, and it turns out it's k3 h cubed over 8. All right? So now it's getting really accurate. This is Richardson extrapolation. And what you do is, of course, that you call this something new, namely n3 of h. And that n3 of h can be written as, we're going to write it in this form, so it's actually the more accurate one, minus, and there's going to be 4 minus 1. There's a, the reason we write in that form is that it's going to be exactly like this formula, but dividing this by 3 instead. So general formula, when all is said and done, I have on the slides, it's going to be, well, there's some notation here, but it's the more accurate one, plus the difference dividing by some constant. You can see that I can keep on going, right? And this can go on forever. You can make really accurate ones here if you want to. But the setting is that you got to do a series of them to get all these numbers out. But let's do just one step with a little silly example. So a silly example would say you have h equals 0.1, right? And the n1, I have some notation issues here, but the n1, so to speak, namely the first h, is going to be when you do just f of h minus f of 0 divided by h. Remember, this was the bad forward derivative that we did before, and we're certainly not happy about it. But we can compute another one by doing h half, right? And we know that this is a first-order convergence scheme. So you should immediately know that if h is small enough, which it is, this should be about 1.025. Because that's what it means to have a formula approximating something, in this case equal to 1, and the error term scales with h, right? So that's, we knew that would happen. Now, of course, you might want to keep on dividing h, but let's say we don't know that. So we can now compute an n2. What this says is that it's really a great idea to just take 2 times the more accurate one minus the less accurate one. And indeed, that's incredibly much better. About 1,000th of an error, right? Without me really doing anything but just subtracting those 2. What do I need to do in order to demonstrate this? Now I have this guy, n2, right, of h. But if I want to eliminate more, I need more data. I need another data point. I need this guy, right? So I do the same thing as I did, but with h half. Remember, I already have this guy, n of h half. So why don't I just do another n of h quarter, play the game here, and then I'm going to get a new n2 for half the h. So in terms of this language here, it's n of 1/3. That is going to be just plugging in a quarter here, right? And it's still pathetic. It's about a quarter now of the initial 5% error, but it's not good. But what I can do with that is that I can produce an n22 using these 2 most recent ones here. And it's, of course, even better. But I'm still not happy. Because what I did now is that I have an n21, which is, so you see the issue with MATLAB versus math code. I would like to call it n2 of h, but that's a function in MATLAB. That notation doesn't work, right? So I'm calling it n21, and you'll probably get confused. But that's the issue with naming. I have an n21, which is this. And then I divided h by 2, and I call that n22, which means I can use this formula to kill yet another term. And the formula in this case says you get to take 4/3 of the more accurate one minus 1/3 of the less accurate one. And now it's 5 times 10 to the minus 6 error. So this is pretty remarkable because I didn't ask where you got these first 3 numbers from. Maybe you did a lot of work, and the best you could do was to come up with a first order. This is a silly example because we have so good formulas for this. You have to pretend, and you'll see examples in the next chapter actually, that we just work very hard in order to get these numbers to be first order accurate. And you can just plug it in here and make it so much more accurate. The general formula is again this. It's actually nice to write it in terms of this, that you get the more accurate one plus the difference over a number. And that number is going to be 1, 3, 7, etc. This table illustrates the entire process. I computed an n1 of h. It was the worst number I had. I divided by h by 2. It got twice as good. I divided by 4. It became 4 times as good. I can even divide by 8. I didn't do this. But anyway, you run your algorithm, your method 4 times, and you get this sequence of linearly converging values. You're not happy. You can use these 2 to produce an n2 of h. That's what I did. And it's much better. But you're not happy. So you use these 2 to produce this guy. And now you have 2 of these guys, which means you can use the formula all over there to produce that guy. And I did that too. But why don't you keep on going and you use these 2, and you can see how this can become a triangle scheme like that, right? So you can develop more and more accurate formulas. And this is it. I have a little demo that you can look at if you want to doing basically what I just did. Richardson demo. I don't know if you appreciate it. It does exactly what I did, but with bigger h's and vectorizing in MATLAB. So you might want to think of what I'm doing here. I'm doing all of them. So I'm doing a bunch of h's. Okay? 4 h's, bigger ones than my example. And I compute a bunch of these first-order approximations. And you can see they're completely horrible because h is big now. These are supposed to approximate 1. But it's going to work out fine because we're going to improve them. But of course, none of these, except maybe the last one, would be even close to acceptable for predicting the actual derivative, which is 1. Now, here's just a MATLAB thing that you might not like, but you might also enjoy it. I do all of the n2s in one sweep. Because in MATLAB, we can write these vector expressions. And if you think about it, what I did to get this number was exactly what I did to this number. And of course, it's going to be exactly what I do to that number, namely this formula. Right? So in MATLAB, you can do them all in one sweep. And you just have to think about my 2:n and 1:n minus 1. But in one language, you have one that is more accurate and another set that is less accurate. And they are coming out here, and you divide by 1. So you can look in that, but you can keep on going. And you can do the next sweep, which improves of those. And finally, you're getting really accurate. Not as accurate as my example, because I set h to 0.1 to start with. But this is really accurate. All right, nice, simple technique. We'll come back to it later, and you'll have some exercises on it. But just one point here is that what if you have a quadratic to begin with? Is this a good idea? Well, you need a new formula, but it can be done. So if there are no h terms, why don't you just kill the h square? So then you can get even faster. So suppose that you have an expression n of h, or some algorithm, whatever, approximating m by h square accuracy. Then the formula ends up being just slightly different. There's a 4 to the power down there, and you can start killing the h2 term instead. So this it's also a powerful thing. You can accelerate things that are not just linear. Of course, it's the same technique. In a way, it's just extrapolation, elimination. It's the same game as before, but in a different setting. All right? Have you seen that before? Probably not. Pretty standard material in numerical analysis, but it's nothing they talk about in calculus exactly. All right, think about it while I start drawing about integration here. By the way, in terms of the order of things, this Richardson extrapolation has nothing to do with this chapter. It's here because we're going to use it. But it's a technique that might as well have been back in chapter 1 or something, when we did more general techniques, order of convergence of functions, etc. Right? They just decided to present it here to spread it out and put it where it's needed. But I'm not differentiating anything. I did in my example, but the Richardson extrapolation doesn't ask for anything like that. It really just asks for series that converge linearly or quadratically, and it's improving them. But I think they are pedagogical by spreading it out a little bit. Anyway, let's start look at integration. Numerical integration. So what's the setting here? The setting is that you have a function, f of x. You have a left endpoint A and a right endpoint B, and you want to numerically approximate the integral from A to B of f, which we often draw as this area here, right? All right, how can we do that? So you can start thinking from scratch. You can remember stuff from calculus. For example, one obvious thing is to take the midpoint and just multiply by the width, right? That's called the midpoint rule, I think. Yeah. And we're going to look at something that is, you would think it's better, but it's actually not. Drawing a straight line from there to there, and it's called the trapezoid rule. So we can do those simple things, and those are going to be special cases of what we do, but we're going to do much better. But what can be said in general about this? So if you see the pattern of what we're doing, I don't think you're going to be too surprised that I'm going to fit a polynomial to this curve. Okay? Because that's what we do all the time. It's exactly what we did when we differentiated, or when we interpolated for that matter. So we can turn it quite general. Let me just show you a very general setting that if you choose 3 points, x0, x1, and x2, and we will never choose these points because they're really bad, but just to show that we could do it, you could imagine evaluating f at those 3 points, right? And fit a quadratic. So that quadratic might look like this. And now it's getting messy. But how do I approximate the integral? Remember, this was one of the motivations for chapter 3 being almost entirely about polynomials. Why do we like polynomials? If this is a quadratic, it's very easy to do stuff with polynomials. For example, integrating a polynomial is very easy. So now you integrate that quadratic again, and you have an approximate value for that integral. Maybe it's good. Of course, we're not going to do that. We're going to derive formulas that are super short and nice, but this is the principle for them. So that's the idea. Turns out that these will all be linear. So what we will do is that we will try to approximate these integrals of f of x from A to B of the form that we evaluate f at a bunch of points, 1, 2, 3 points, and they're going to be multiplied by numbers. And we'll see what they are, but in general, this is what's going to happen. If you choose a bunch of points, I'm going to ask you to evaluate f at those points, and I'm going to give you magic numbers that you multiply with, and you get an approximation to the derivative. That's it. And of course, I also want an error constant, right? As always. And whether you use it or not is up to you. But in many of our examples, we want to show that we can actually put a number on how good this is. So let's see what we're going to do here. Look at this that we have here in the slides, numerical quadrature. The general expression is going to be something like this, that when you have the Lagrange polynomial, which is really just a sum of f times L, and you integrate that, what's going to happen? So remember, we write this, you see this Lagrange formula coming back over and over. We write a polynomial as a sum over function values times these magical L's, right? If you want to integrate that, it's still a sum over function values times integrals of L. The only thing that depends on x in your polynomial is the L's of x. So in other words, the integral of f will be approximated by the sum of of these f of xi times some numbers. And those numbers are really just the integral of these l's. Very simple. So all you have to do is to integrate l's. Now, of course, we want the error term as well. What is that? Well, I don't know. So what I wrote here is really just the integral of the error term. And you might have to play some special rules or some special tricks in order to get it out. But let's look at the special case. That's probably good. In fact, I'm going to look at the trapezoidal. So what do we have for the trapezoidal? So this is maybe one of the first cases you would consider. Trapezoidal rule. Or in fact, as I said, I think the first one you would consider is only 1 point. And that would lead to this rectangle midpoint or something, right? But for some reason, I go straight for the trapezoidal here. So the setting is pretty clear. You're saying that why not pick x0 equals a and x1 is equal to b, and you're done. That's the same thing as saying there's a point and there's a point. What did I do with my points? I fit the polynomial, right? So that's going to be a straight line. And I'm going to approximate the integral by the area under a trapezoid. And in fact, the way we do it in calculus, and what you should really do here, is to just say clearly, it's going to be f of x0 plus f of x1 half times the width, right? The area of the trapezoid, and we're done. That's the formula, right? But we're not going to be that because we want the error formula, and we want to just show that the general procedure works. So the general procedure said, first we write an expression for this approximant here, which is a polynomial of degree 1. So what we do then is that we have one L0, which was x minus the other points. Remember this stuff, right? And then you had an L1 that was x minus x0. What we said in the slides was that these constants, these coefficients here, is really just going to be the integral of those l's. So that's how you come with the formula. So the a0 is going to be the integral from x0 to x1 of L0. Right? And it's a straight line, so it's not that difficult. Let me just do it. 1 over x0 minus x1 comes out. This becomes a quadratic primitive function. Plugging in x0, x1. When you plug in x1, you kill it. So this is just equal to 1 over x0 minus x1 minus x0 minus x1 square. I know you think it's a lot of work for something we already know. And now we kill one of those. It ends up being minus x1 half. And why don't we take away the h? So this is the number we get, the sign there. We're often going to call this h, just like we've done before. So this is h half. Sorry about the 2b. H half. Okay? That shows that the first number to multiply f by is going to be h half. Very simple, nice rule. You don't have to do this fitting anymore. You get a formula, and you'll keep on using it. I don't think anyone will be surprised that the next one is also h half, if nothing else for symmetry reasons or whatever you wish. But I'm not even going to do it. A1 is, of course, integral of L1 of x. And you just do this again, and you get again. Okay? So, we certainly got the calculus thing out of it. The integral from a to b is approximated by h half times f of x of f of the left point plus h of half times f of the right point. We knew that already. I guess what we want is the error term. So let's look at that. It's going to be something like the following. This e, and in the slides we have this general expression. E of f is equal to this big thing. And we'll see how we can simplify that out. Let me just write it out for this case. So n is equal to 1. We just have a simple straight line here. It's going to be an integral like before. There's going to be an unknown evaluation point of the second derivative of f. And then you get this product from the Lagrange, which is x minus x0, x minus x1 dx. All right? And you should realize I didn't do anything. This is the error term from Lagrange, and I just put an integral sign in front of it. So we're going to have to be a little smart. But so far I haven't done anything. I think the message here is that when you have these interpolating Lagrange formulas with error terms, you can derive a lot of stuff. And whether it's a lot of tricks to actually get it out, this is kind of the error. But it's not that useful. What you like to do, so what is this? This is kind of, I mean, if you know f double prime, you could, we could play our usual game of replacing this by a big number. And then we could try to optimize this. But it's kind of an integral, so it depends a little bit on the shape of that. So there is a nice trick we can play. And this is, I think, the only reason that they taught you back in chapter 1.1, 1.2, 1.4, Mathematical Calculus Review. They mentioned the weighted mean value theorem. Remember that? That you cannot just replace an integral by some point in between, but you can have two functions. So that's what you can do that here. It turns out to be nice. So if you call this a g, and this is a function that does not change sign on your integration interval, and it doesn't, which you have to think a little bit about to realize, but that's because x is between x0 and x1. So if this guy will actually be negative for all of those values, and this guy will be positive for all of those values. Sorry, the other way around. This will always be positive, this will be negative. So it doesn't change sign. So we can get this out by going back to a little reminder here, the weighted mean value theorem for integrals, which said that if you want to integrate from a to b fx gx dx, you can pull out the f from this at some appropriate number, and left you get just the integral of g. And this is for some c in the interval. Let's see, between a and b. And it's important to mention the other thing. If g does not change sign on AB. All right, so you might remember that. And now is the reason. Now you'll see the reason that we learned it. It's just so we can get a nice formula out of this. Remember, our previous formulas were kind of nice for the error term. It was just f second prime of psi times a number, right? We like to do that here. We don't like to leave it in this form. It's too much work when you're going to use it. So let's see how we can actually use that formula to simplify it. And it's pretty obvious what I'm going to do. This is the f that I'm going to use down here. I'm going to pull this guy out and say that whatever it is, it's a function of psi of x, right? So, it can be replaced by some other psi. And the rest, I can actually integrate, because integrals of polynomials are easy. So you kind of bring out the part that you don't like, and you get the following. So this e of f ends up being second derivative of psi. There's a divided by 2, and you get this integral of just x minus x0, x minus x1. And this we can put a number on. Namely, this we just leave. That number is going to be, you have x squared, which is x cubed third, right? Then you have that linear term. It's going to be plus x0 divided by 2 times x squared, x0 times x1, and you integrate it, and you plug in x0 and x1. Look, don't worry. I mean, you know how to integrate this, right? So when everything is said and done, you get this expression out. Isn't that a nice form to report the error in? Wouldn't you be happier if you're supposed to estimate the error in the trapezoidal rule if someone gave you that rather than this? We could pull out the psi, which is reasonable to do because we don't know what it is anyway. And then we can actually do the integration of this parabola already. and out pops a lot of things. And it tells you a lot of interesting information, like before. What happens if you divide h by 2? Well, this is what happens. You get 8 times more accurate integral. But more importantly, which class of functions is this formula perfect for? You could have seen already from this figure that for straight lines, polynomials of degree 1, it's a perfect formula. Not too interesting, right? For parabola, it's not perfect. And indeed, here's the second derivative. So that's what comes out of it. Anyway, summarizing that formula, here it is. The formula is easy. We have to work more for the error term. But when you have it, it's an extremely useful expression that tells you how you can approximate with trapezoidal rule. All right, we're not happy. It's not accurate enough. So we're going to move on. And I'm sure, actually, when I teach Math 1B, we do Simpson's rule there as well. So you've probably seen it. This is a really powerful method. Remember what I said about the cubic splines, that third-degree polynomials seem to be great compromise for a lot of things. And Simpsons are kind of second degree, but it turns out to be one extra higher accuracy. So there is a sweet spot where these methods seems to be most useful. And Simpson's rule is more accurate than trapezoidal, but it doesn't overdo it. And first, let's just say what it says, and I must have forgot something here. I'm pretty sure there should be an F, right? Yeah, of course. So you see that the pattern is exactly the same, namely that you're really just grabbing points. In this case, there seem to be 3 points, and you're evaluating F. In this case, the numbers are h third, 4 thirds h, and h thirds. Okay? We do whatever magic in order to get this error term out. And you see that this is a much better method. It's an h5 instead of h3, and it's an f to the 4, which means in particular that if you run Simpson's method on a cubic, you'll get the exact answer. It's good to know. So we'll come back to that later. Let me derive Simpson. There are various ways to do it. In the book, they do it in a way that I'm not going to do, because it's a little confusing. They do it with Taylor. It is a, I think, pretty short way. You might not agree, but let me show how I want to derive it. And we will actually get the error term out as well. No more trapezoidal. So you see the end result is going to be really short. 3 numbers, h third, 4 thirds, h, and 1 third, and an error constant. And by the way, I'm going to assume a certain form of the error constant, but you'll see how that comes in. Simpson derivation, or alternative derivation compared to the one in the book. So here's what I'm going to do. Simpson. So let's first see what the setting is. It seems to have 3 points, A, B, and A plus H. So what they seem to want is the following. There's B. Here's A. They're going to use f of A, and they call this x0. They're going to use f of B, and they call this x2. And they have another point in the middle that they call x1. And it's exactly h away from A, right? So they seem to define h, just like before, to be the distance between the points. And they have 3 points, and they evaluate these 3. All right? That's the setting. Can I just, I'm going to do some quick tricks to make this proof a little less annoying. Can I convince all of you that if I move this entire graph to the left, I don't change the value of the integral? If I take the entire function and just move to the left, and A and B, of course, as well, it doesn't change. Integrals are translation invariant. It doesn't matter where they are if you just move it. So I can just as well consider the integral from minus h to h of fx dx. And if you don't like that I'm integrating from minus h to h, you just add a to everything, plus h, I guess. Okay? So that's the first little step I'll just make. And here's the thing. I'm going to assume it has a certain form. I want it to be a sum of constants multiplying function values. So why don't I just say that? Remember we said all these formula will, and you can actually show that this is the only thing that makes sense to have a linear expression like this, because integrals are linear in the first place. So this alternative derivation will just assume that, and then we'll derive those expressions. And it's quite easy. And in fact, I will do the same thing for the error term. The only thing I will do is to assume that it depends on the fourth derivative at some point xi. OK? And I know this seems a little iffy compared to the rigor from before, but we get the formula out, and if it makes sense, the numbers will work out as well. How do we do this? So this is a technique we will use a lot. We will we will force the formula to be accurate. So here's a question. Let me just, this is kind of easy to see. What if you integrate the function a constant? Let's say f of x equals 1. What do you expect this formula to do? It's reasonable to expect it to give the exact right answer, right? If it doesn't, it would be really bad. If you can't integrate a constant exactly, you're in big trouble. Do you see that that gives me an equation here? Because if I put a constant here, let's say 1, because it doesn't matter what it is. This integral is 2h. But this here is just going to be a0 times 1, plus a1 times 1, plus a2 times 1, plus 0. There's no error, because I assumed it has a fourth derivative error term, right? So you see that I just said that a0 plus a1 plus a2 better be equal to 2h. Or my formula would not even integrate the constant correctly, which it can be a little philosophical whether that's needed or not, but all the formulas we look at will be exact for polynomials up to a certain degree. So I'm claiming that if you set f of x equals to 1, you're getting an equation that says 2h equals a0 plus a1 plus a2. 3 coefficients, 1 equation. And you can all figure out what I'm going to do. I'm going to say, well, the trapezoidal rule was perfect for straight lines. And Simpson doesn't want to be worse, right? So it's going to say, I'm also going to be perfect for straight lines. What is the true integral of a straight line? Well, now you're happy because I choose minus h to h, because that's an anti-symmetric function. So this is really just 0. If you doubt me, just do the primitive function. But here now we're getting minus h a0 plus 0 plus h a2. Okay? So I got a new function. In fact, it's just saying that a0 is equal to a2. But good news, I have 3 points. I can use one more equation. And that's what's going to make this formula better. In fact, it's better than we deserve. It's automatically going to give us one more term. But if you plug in x squared, you got to compute this integral. But you know how to integrate x squared. From minus h to h, it's going to be 2h cubed thirds. And we want our formula to do the right thing for this. And if we plug in this in our formula, we get h squared a0. We get a 0. And we get h squared a2. All right? In fact, if we forget about the error term, I now have everything I need to actually get the formula. You see that? 3 unknowns, 3 equations. I should be able to figure out what those coefficients should be. And it's kind of easy because, so this is a linear system of equations. It's clear that a0 is equal to a2, right? And if you plug in that in the bottom, if you plug that in here, you get 2h cubed thirds equals h squared a0 times 2. All right? Or in other words, a0, which was equal to a2, is going to be h thirds. And now you go back to the first equation to say that h1 is 2h minus a0 minus a2, and that's 4h thirds. And we're done with the coefficients. Isn't that nice? I know there were some tricks, but you can imagine that this really saved us a lot of work. But let's look at the error term. As it turns out, why don't we just keep on going? we don't think we're going to be able to do it because we had 3 equations and 3 coefficients. We don't deserve anything more. In fact, the cubic now should be wrong. Turns out it's not, because what happens here is that when you integrate a cubic, it's also an anti-symmetric function. You get a 0 here. So then you're getting 0, and you're getting equals to minus h3 a0 plus 0 plus h3 a2. We already said a0 was equal to a2. In fact, we decided now that they are both equal to h thirds, right? So guess what? We're satisfying this equation for free. I mean, these we worked hard to satisfy these 3. We chose our coefficients to satisfy those, but we're getting an extra one for free. So Simpson is really, it's symmetry reason. It's because of the symmetry. If you move this point away from the middle, you lose this. So don't do that. Anyway, this is nice. The next one is gonna not work though, but that will give us the error formula. So what this equation is going to say is now you have to compute the integral, and it turns out to be 2h5 fifths. Okay? And our expression is saying that h for a0 plus 0 plus h, there's a minus sign there, remember? No, none here. Plus h for a2. And they're still the same, of course. And now you can see the little bit of hand waving in the fact that I just chose what I wanted this to be. But that's because I know now that my formula will not be perfect. You can actually see that it won't by just plugging in h third here. So I better need something else. Otherwise, I can't satisfy it. That's the motivation for making this a 4th derivative. But that was hand waving. I'm not saying it wasn't. Anyway, given I'm doing this, it's pretty easy. What is the 4th derivative of x4? 4 times x cubed, 4 times 3 times x squared. Do you see that it's 4 factorial times 1? And there was a k. And what's good about this? This gives me k. And then I'm equally quickly done with this as before. So anyway, this leads to one more line. 2h5 over 5 equals, remember 8, these were given, h third. So just plug it in. It's going to be 2h4 times h third plus 24k. And this apparently leads to k being 1 over 24 times 2h5, something like 1/5 minus a third. 1/5 minus a third. And at the end, it's going to be minus h5 over 90. No, this was not a trivial step. I just jumped over steps. It's just algebra. Wasn't that nice? Let me write the entire formula so we conclude it. Integral from minus h to h of fx dx is equal to h thirds f of minus h plus 4f0 plus f of 1, plus the error term, which is minus h5 90ths times the 4th derivative of f at some psi. This is the final conclusion. And again, if you don't like that it's from minus h to h, use a standard calculus property of integrals and move it to wherever you want it. And in general, we will, of course, do that and write it in the form in this form. All right? A little iffy. I can see you guys being a little upset about this assumption, right? But given the assumption, I think you can all see what I did. I'm enforcing it to be exact for a bunch of polynomials. Turned out I get one for free, but eventually it doesn't work out, and that leads to the error term. And in fact, you could argue that leads to the assumption on the form of the error term. This is not a proof. This is that if it has that form, A0, A1, A2, and K must have these values. What we did before with the trapezoidal was rigorous. It was a proof all the way down, right? Because it was based on these Lagrange polynomials. All right, but you can, of course, show that this is the case. If you want to. Now, this concept of saying which polynomials is it exact for is so powerful that it's really a way to classify a method. And it's one of the first things you ask about this method. What is the degree of accuracy or the precision of a method? And it's defined to be exactly this thing we talked about before. It's the highest polynomial that it's exact for. All right? So what is the degree of precision of, where is our trapezoid? What is the degree of precision of the trapezoidal rule? The highest degree polynomial that it's exact for. Straight lines, right? So that's 1. If nothing else, look at the f2 derivatives in the error term. It means that a quadratic polynomial is not exact. What is the precision of the Simpson rule? Well, we did it very explicitly, saying that it's actually exact for x3. So we're done here. It's 3. But if you're just given the formula there, you see that there's a fourth derivative of f, which is 0 up to polynomials of degree 3. All right, do you want to general? So this is an extremely powerful method. It's used a lot. Both of them, actually, trapezoidal as well. But you can, of course, do a lot of different things. So here's a generalization. The Newton-Cotes formulas. They just keep on going. Okay, so what did we do? We put points spread out in, let me kill this. So we put points either at the ends or the ends and the midpoint. So what we've done so far is that we did trapezoid, a point there and a point there, right? Then we did Simpson, we put an extra point in the middle. If you just want to keep on going because you never get tired of this, what's the next thing in that series of patterns? You would, of course, put more points. So in general, you would put n points. Let's see if I get this n correct. N is equal to 1. Yeah, OK. So we go from x0 to xn by having, of course, then appropriate steps in between, x1, x2, x3. And it just leads to more and more complicated formulas. But it can be done. In fact, the coefficients are not derived here. They're simply just saying that it can be done. OK? So these are called the closed Newton-Cotes formulas. And you'll see why it's called closed. So trapezoidal rule and Simpson are special cases of the closed Newton-Cotes formula for n equals 1 and n equals 2. Now, here's one thing I mentioned before, the midpoint rule. For whatever reason, you might choose to say, hey, I don't like A and B. Why don't we just skip those? And you put n points in between. And those are the ones you use. Well, that's the open Newton-Cotes formula. And let me draw the general one here, which then sets x0 hn, like that. And it goes up to xn. And it puts a polynomial through these, but not including the A and B. It's just a choice of points. The way I started, remember my ugly figure here where I put 3 points. They were not in any pattern special. So the question is, what are these? And in fact, in a few sections, we'll come to something called Gaussian quadrature, which asks the question, what are the optimal points? And the answer is none of these. But this, at least just for completeness, it leads to a whole set of formula called open Newton-Cotes. There's a very important special case here. If you're setting n equals to 0, you're getting 1 point, right? x0. And it's going to end up being right in the middle. That is the famous first thing you learn in calculus, midpoint formula. And it's actually quite accurate. So here it is, integrating from, well, whatever my notation is here. But integrating a function, you do 2h, the width times the midpoint. And it ends up also being as accurate as the trapezoidal rule. It's counterintuitive, actually. Trapezoidal rule, you evaluate left point, right point, you draw a trapezoid. You would think it would be much better than just doing a midpoint and doing a rectangle, right? Turns out, again, symmetry reasons, that they are almost exactly the same. Same order of accuracy. Anyway, I'm sure you need to see that this works. What do we have? E to the x. Guess what? I'm going to integrate e to the x. Using what? Trapezoidal rule? Well, it's pretty obvious, right? You choose. So right now, we're really just doing the entire integral, and that's something I want to emphasize. It's really just one integral when we fit one polynomial. So let's say that the integral should go from 0 to 0.1. Okay? Now, actually, to compare, let's go to 0.2. What would the trapezoidal rule do? It would do f of the left endpoint plus f of the right endpoint half times the width, right? That's what a trapezoidal rule does. I'm now in my example now. I should probably explain my example. F of x is equal to e to the x. A is equal to 0. B is equal to 0.2. Okay? So the trapezoidal rule says that. What is the true answer, by the way? Now you see why I like e to the x. Because the primitive function is e to the x. So this is the true answer. Looks pretty good, but it actually looks confusingly good, as you see. The 14 is repeating itself. Did I make something wrong? It's almost too perfect. Anyway, let's assume this is the true answer, because it's supposed to be, right? So let's do Simpson now. What would Simpson do? You actually have to be a little bit careful, because Simpson is dividing h by 2. Remember, Simpson takes these 3 points. So I just did trapezoid. I put a point there. And of course, the h is the distance, 0.2 between them. Simpson will put a point in the middle, and h will now become 0.1. So let me not redefine h. Let me just write Simpson as it was a third in front of everything. It was f at the left endpoint plus 4 times f at the midpoint plus f at the right endpoint. All right? And there has to be a width as well. And it's actually an h third in front of it. And that's confusing here, because that's actually the half h. So that's going to be 0.2 times divided by 2. So a little hard to get it right. I think this is correct. Let me see. Looks good. And now we see that it was just weird magic that trapezoidal rule reproduced all these. That's actually really. There is probably a reason for that, but you can see that it's wrong already in this digit. So trapezoidal is not that accurate, while Simpson nails all the digits up to there. And this is what we expect from a more accurate method. But it's pretty cool. It means that for many practical purposes, you could actually use this number instead of the previous one. And remember, this seemed easy just because I chose the simplest function in the world to integrate. Let's say you choose, if you just do minus x squared there, I cannot even check the result, because it's impossible to integrate. But how will this change? Well, you would just do minus 0 square minus square minus square. This is the integral, an approximation of e to the minus x squared from 0 to 0.2. And it is what it is, right? So that's pretty cool. Anyway, too much information? A lot of this is little review, right? So not too bad, I hope. There's going to be a nice pattern to what we did before now, even if I won't have time to finish it. Namely, I'm going to say, do you think this is a good idea for a function that looks, let's say, like this? Remember how we ended chapter 3 by saying, look, now we know how to put 10 degrees polynomial through 11 points, right? It's just that we're not going to do it. It's a bad idea. So the same thing is going to happen now. The way we did was really just fitting one polynomial. So if you have a function that looks like this, of course, the rules we've talked about, I mean, trapezoidal would be a disaster, right? Just looking at it, it's not well, it might accidentally be good, but we don't trust it, right? And indeed, all those numbers, the error terms would say that it's bad. So all we learned so far is why don't you do a Newton codes and throw in a lot of points? You could do that. But then you would be doing the same mistake as we said about polynomial. You don't want to fit a 10th degree polynomial to this and integrate. What do we do instead? Subpolynomial. Yeah, so the first would be, it's just like, I'm just presenting it like I did with the splines. Just put a spline to it. Turns out that that could be done. It's not that needed. We did a lot of work with the splines to get this high degree of smoothness between the polynomials. There's no reason to do that when you're just computing an integral. You don't need the smoothness. But it's the same idea. Split it up in subpolynomials. That's the key. So that's called composite integration. So instead of doing all of those, you're going to split everything up like this. And then you, for example, the composite trapezoid method is not a big surprise. It's going to take this interval. So if this is x like this, it's going to put a trapezoid for this guy, right? All right? So that's the trapezoidal method for that little subinterval, x0, x1. And then you forget about that, and you go to the next one and do a trapezoidal. And this is the method. And here's going to be a little inaccurate, but it's not too bad. You see the idea? That's the composite trapezoidal method. And actually, it can be quite efficient. But this turns out to be a much more powerful method. So what can you do now if you're not happy? You can, of course, throw in more points, right? If you think that this was a little rough to approximate this whole curve here by a straight line, just divide h by 2 and you get more intervals, right? You can also go up one step to Simpson. And that is probably the most popular method for integrating, the composite Simpson. Composite meaning that you're just splitting up the interval. What is the property of integrals I'm using here? When I say that there is nothing, I mean, you could argue that I'm approximating the entire function by this piecewise like that. But really, what I'm doing is to say that an integral from there to there is really just equal to the integral from there to there, plus the integral from there to there. Right? I'm just splitting up the integral from a to b into a to something else plus something else to n, right? That's all I'm doing. So that's the whole idea here. It's called composite rules. We're going to look next time to see where these numbers come from. Turns out that it's actually a lot of smart things happening here, because this point here you will reuse for the left and the right. So it's a pretty efficient method. But you can look at it yourself. I'll follow up on it on Thursday. Thank you.